Thanks, Abhishodh. So let me also begin by thanking the organizers for the invitation and for putting together this really exciting workshop. It's my first time to this particular campus of ICTS. The last time I was here, they were still housed at IISc, so it's certainly very exciting to be here. Okay, so if you look at my title, for better or for worse, it has all the buzzwords that we like in contemporary times. But as the talk progresses, hopefully it will become clear how each of these buzzwords, so to speak, play an important role in the story that I'm about to tell you. Now, from a pragmatic point of view, I could have come up with a better title, which is how high can the superconducting TC be? Okay? This is not a new question. Many people have addressed this over the past many decades. And we want to revisit this question inspired by actually some very interesting developments that I'm sure most of you have been familiar with at this point of time, which is related to so-called flat band superconductivity in various van der Waals-Moiré structures. And hopefully I'll convince you that we have found something very interesting for a somewhat artificial model, but which we can study very reliably using certain numerical techniques. So let me actually begin by thanking my collaborators. So the work that I'm primarily going to tell you about today has been done in collaboration with Johannes Hoffmann, who's a brilliant postdoc at Weizmann, and he's the one who did all the numerical work, and with Eresberg, my friend and longtime collaborator, who should be on his way to ICTS right now. Now, if time permits, I'm also going to tell you about some very interesting experimental results on twisted bilayer graphene, and this was work done in collaboration with Senthil at MIT and with Pablo Yarillo Herrero's group at MIT, and three of his brilliant graduate students, Yuan Tsao, Daniel Rodin, and Oriol Rubis. So the work that I'm going to focus on mostly actually just appeared last Friday. Okay, so let's get started. So this is the post-lunch session. I know a lot of you don't feel like sitting here. So what I want to do is start with a sort of a quiz. Okay? But before that, let me just, in order to set the stage, just remind you that lots of interesting things have been happening in the field of 2D superconductivity over the past almost 2 years, which of course started with this amazing discovery of superconductivity in twisted bilayer graphene near these so-called magic angles. But since then, we have encountered superconductivity in other van der Waals structures such as ABC stacked trilayer graphene and even twisted double bilayer graphene, which I'm assuming we'll hear a lot more about from Ashwin's talk tomorrow. All right, now one of the things that's common across all of these different platforms is the ability to engineer and control the electronic band structure and to make them relatively flat so that the interactions somehow end up dominating over the characteristic bandwidth in the problem, okay? So now the question that we want to address and the quiz that I want to give you is the following. So imagine, so this is just a cartoon of the typical band structure that we might be interested in. So what we have here is a set of active bands, which have a bandwidth denoted W, which are well separated from all the other bands in the problem, which are inactive, so to speak. And these active bands are separated from these inactive bands by some energy scale. Let's call that energy scale delta gap. Okay? And we are interested in this particular band when it's partially filled by electrons. Okay? And the regime of interest to us here is the following, where the characteristic bandwidth associated with this isolated band is much smaller than the interaction energy scale, which is also much smaller than the scale associated with this gap to other inactive bands. Okay? So the question that we want to address is what happens when you partially fill this really narrow bandwidth band and turn on interactions. Okay? So the first question, of course, we want to address is what is the ground state? Now, a priori, this is a very hard question to address. There are numerous possibilities. So for instance, it could be a superconductor, insulator, various forms of charge density waves, and yeah, the list is in principle endless. But suppose I make the model somewhat artificially. Of course, in reality, we are dealing with repulsive interactions. But let me say that, let me get started with attractive interactions. So that superconductivity has some chance of winning. Okay? But then what I do is I take the limit of this bandwidth going to 0. Okay? So now the question is, okay, I've started with some attractive interactions. Maybe superconductivity can emerge somehow, but what will be Tc in the limit where this bandwidth goes to 0? Okay? This is obviously a non-trivial question to answer. There's no bare kinetic energy, so to speak. The problem only has interactions. Now, this is especially tricky to address because when you don't have any bandwidth or kinetic energy associated with the fermions to start with, there's no, so where is the Cooper pair kinetic energy going to come from? Okay? In some sense, there's only one energy scale in the problem, which is the interaction. Now, said differently, could have also asked, we're dealing with a 2D system with potentially some form of superconductivity. What energy scale sets the superfluid stiffness? Okay? And finally, things become a lot more interesting when these isolated bands also have some kind of topological character. Okay? Of course, I don't need to emphasize the fact that when these bands have topological bands, this kind of cartoon picture is very reminiscent of the classic quantum Hall problem, where you want to project your interactions to the lowest Landau level and study the ground state properties. Now, so the reason why topological bands become interesting here is because if you think in terms of a real space picture, you can't, if you project really to these nearly flat topological bands, you don't have a local, exponentially localized Wannier representation for these bands in real space. So you might think that the Wannier function so defined will be fat. So you can get some non-trivial overlap even between the Cooper pairs that emerge out of these bands, even in the limit where this bandwidth goes to 0. So there's potentially interesting physics associated with superconductivity if it emerges in this particular limit of the bandwidth going to 0. Okay? So, in the interest of time, I didn't actually post this as a quiz, though I must say that in the past few months, ever since we started working on this project, every time I've brought these questions up with my colleagues and friends, it's obvious that there's no obvious answer to any of these questions. So hopefully in this talk, we'll study a concrete model and try to address many of these issues. Okay, so, and in my opinion, in some sense, these are the key questions that we need to address in order to shed some light on flat band superconductivity, okay? All right, so with that, here's a quick outline for the rest of my talk. So as I mentioned, what we are going to study is superconductivity, or the possible emergence of superconductivity in narrow churn bands, okay? So this is one kind of a topological setup that we're going to deal with at strong coupling, and I'll define later on what I mean by strong coupling. And then if time permits, I'm going to tell you about these transport experiments in twisted bilayer graphene, which show certain evidence of strangeness. Now, many of you have probably heard of this term called the strange metal, which shows up in many strongly correlated systems. And by walking you through the experimental data, I'll try to convince you that there's definitely something strange about this transport. Now, this is something I actually won't have time to talk about, but quite interestingly, a lot of these kinds of features also show up in certain exactly solvable models we've been playing around with, except that those don't have any topology, so to speak. And I'm happy to talk about this offline. Okay, so before I introduce the model, let me just spend 30 seconds on the philosophy. So as I discussed, we are dealing with an intrinsically strongly interacting problem. So there are no control theories, so to speak, for describing the universal phenomenology. In principle, one could do mean field theory. And if you only have one interaction scale in the problem, which is you solve, let's say, the BCS gap equations, you may find a TC that is given by U, but it's totally uncontrolled. There's no reason why it should work in a regime where U is comparable to or even much bigger than the bandwidth. The same is true for all weak coupling type approaches. So we don't want to just go back to doing these kinds of things. So what we're going to do instead is work with a somewhat artificial looking model, but explore it in a solvable limit, because at the very least, that allows us to address certain proof of principle questions. So just to give you a list of things that we're interested in, we want to understand what is the nature of the normal state above the superconducting TC, if there is superconductivity, what are the competing ground states, and ultimately, the most important question, what sets TC in this limit of the bandwidth going to 0? So in order to solve this problem, what we're going to do is we're going to take topological bands. In particular, we're going to take topological bands that have a finite churn number, but in a time reversal symmetric model. And then, because we are most interested in looking for superconductivity by hand, we're just going to add local attractive interactions, okay? So an attractive Hubbard U model, if you wish, and then solve it using determinantal quantum Monte Carlo, okay? So at the very least, that should tell us something about how all of these different ingredients, topology, strong interactions, and narrow bandwidth gives rise to these different phenomenology. Okay, so with that, let me introduce to you the basic model. In the interest of time, I won't describe the model in great detail because it's ultimately a refinement of a model that was introduced a long time back by these gentlemen. Okay, so it's a square lattice model with a certain pattern of pi fluxes encoded in these patterns of the nearest neighbor hoppings. There's also some second neighbor hopping, which has some staggered structure. And we also allow for some fifth neighbor hopping. It'll become clear momentarily why we include a fifth neighbor hopping, okay? So if you just diagonalize the non-interacting part of the band structure, you get bands that look like this. So the lower bands that you see in these two different pictures, those have a finite Chern number of +1 for the spin-up electrons and -1 for the spin-down electrons. Now what the fifth neighbor hopping, this red line, if you can see it, allows us to do is to tune the bandwidth associated with these valence bands. So here, there's no fifth neighbor hopping, so the bands have a finite bandwidth. So this is 0.83 in units of the nearest neighbor hopping. But when you make that -0.1, you drastically reduce the bandwidth. Now, in order to characterize how flat or narrow a band is, we introduce this quantity called the flatness ratio, which is basically the ratio of the bandwidth to this gap to the other band. So the bandwidth divided by the ratio between the energy scale between these two bands, okay? So when there's no fifth neighbor hopping, this is 0.2, but when you introduce this, it's essentially 10 to the -2. Okay, so that's the basic model, and on top of that, we are now going to add local attractive interactions and study the phase diagram of this model for different values of the flatness ratio and interaction scale, okay? That's the basic philosophy we are going to do. Okay, so before I do that, I still want to remind you what happens in the classic square lattice attractive U-Hubbard model with just nearest neighbor hopping. Again, this has been studied using DQMC. The model doesn't suffer from a sign problem, and of course, there's a lot of literature on this. I'm just choosing to show you data from this particular paper. So if you look at TC as a function of U divided by hopping, at weak coupling, the TC is basically just given by the mean field BCS estimate of TC. And then when you crank up the interaction scale, ultimately, the TC as determined from Monte Carlo starts dropping, okay? And this is because beyond a certain characteristic energy scale, the Cooper pairs that are forming locally, they lose phase currents. In fact, this asymptotic line that you see, that's just the energy scale associated with T squared over U. Okay? So just arbitrarily cranking up interactions doesn't mean that you can arbitrarily crank up TC. There are two effects that you need in order to have superconductivity, both an onset of a local amplitude and some sort of a phase coherence. Okay, so, and in particular for this model, the optimal TC turns out to be 2% of the bandwidth. That occurs roughly where U is comparable to the bandwidth. Okay. Now, within the same model, there is also a broad regime, the so-called Pseudogap regime, above TC, where you have local, well-formed pairing amplitude whose scale actually increases with U, but no long-range phase coherence. Okay. So the Pseudogap scales proportionally with U, but the TC doesn't. Okay, so this is all well understood, and I don't need to emphasize here how, if you literally take the limit of the bandwidth going to 0, all of these, the TC just collapses. Okay, so in the limit of this particular trivial band going to its flat limit, you won't find any superconducting TC. Okay, so now coming back to our model, we want to understand what happens in the limit where the bandwidth is really narrow and you turn on these attractive interactions. Okay, so the way to diagnose this is, of course, again, to look at the superfluid stiffness, which can be evaluated in Monte Carlo by looking at the current correlation function and a particular limit of the momentum going to 0 while the frequency is 0. So I see that my collaborator has just walked in. So this is what the superfluid stiffness looks like as a function of temperature. Now, this is the result for the flat band, where the bandwidth is 4% of the nearest neighbor hopping, and the flatness ratio is roughly 10 to the minus 2. So what you see quite beautifully is the fact that you are finding superconductivity. The superfluid stiffness is finite, and in fact, it is just determined by the only energy scale you have left in the problem, which is U, as demonstrated through the scaling collapse when the temperatures are in this particular asymptotic regime. See, all of these different curves fall right on top of each other, and so the ratio of the superfluid stiffness to the energy scale is simply given by this scaling function. And for a fixed density, which is what we are showing you the results for here, it just depends on this ratio of T over U. Okay, so this is obviously the bandwidth here plays no essential role. Of course, the scaling function depends on the underlying block wave functions, if you wish, of the non-interacting part of the Hamiltonian, but that's all. Now, in order to determine the superconducting TC in 2 dimensions, we can use the Nelson-Kosterlitz criterion for the universal jump in TC. And if you do that and ask how TC scales with U, what we find is quite remarkable. So this is TC as a function of U. So the 2 different curves correspond to the 2 different bands. So the dashed line is the data for the flat band, while the solid curve is the data for the not so flat band. Okay? Now, of course, as you crank up U, you see that even the not so flat band, the actual value of TC approaches the value for the flat band. And this curve looks pretty damn linear to me. And as you see, you're cranking up U to really large values relative to the bare nearest neighbor hopping, and TC just keeps scaling linearly. Okay? Good. So, of course, as I had already mentioned, if you were doing mean field theory on this model, you would have obtained a TC scaling with U, but there it's totally uncontrolled. Here, this is a numerically exact solution for the full Hamiltonian, and indeed we find that TC does scale with U even in this limit where the bandwidth is much, much smaller than all the energy scales in the problem. Okay. Of course, we can go ahead and actually study this problem as a function of the density. So what we are doing here is just taking this lower Chern band and first emptying it out and then filling it up all the way to the top. So the optimal TC occurs roughly near half filling, and then you find this nice dome of superconductivity. Now I want to discuss what the normal state looks like. In particular, a relevant question that we're interested in is if the state above TC, if that's somehow a metallic state with reasonably coherent electron-like quasiparticles, or is it some kind of an incoherent liquid of Cooper pairs? Okay. So to study this, we look at the spin susceptibility, defined as follows. So here in general, this is a correlation function for this operator O. So if you take O to be just the SZ, what you find is shown here. Again, the solid curves are the data points for the not so flat band, and the dashed lines are the curves for the nearly flat band. And what you see immediately is that there is a characteristic energy scale below which it drops quite dramatically. There's an opening of some kind of a spin gap in the problem, which is, again, reminiscent of some kind of a pseudogap. Of course, at these temperature scales, there's no long-range coherence, phase coherence, so there's no long-range superconductivity. One can also look at the orbital susceptibility to look at for signs of diamagnetism. And indeed, what we find is that already above TC, you start seeing some kinds of diamagnetic response, which is again sign of some kind of local pairing fluctuations. Okay, so already at this point, it's quite reasonable to believe that the state above TC is showing evidence of a spin gap state with some kind of local pairing, but no long-range phase coherence. So now what we want to identify is how this particular scale also scales with the interaction energy scale. And again, so of course we need a diagnostic of how we define this particular energy scale, so we can take it to be the point at which the spin susceptibility exhibits a maximum. So if you tabulate this, again, this is what it looks like as a function of U for both of these different bands. So again, for the flat band, which are the dashed lines, you see this is the old plot for TC, now on this bigger scale, and this is the pseudogap temperature scale. So both energy scales just increase nearly linearly with U, and the larger coupling you go to, this fluctuation regime increases with U. Okay? For the not so flat band, things are not so linear, but again, as you go to higher and higher values of U, they sort of asymptote towards the values for this flat band. Okay, so now we want to dig this a little deeper, and we want to understand what the charge response looks like in this broad fluctuation regime, which we identify as the pseudogap, and what the other spectral features look like. Now, this is going to be a little hard from QMC, which only has access to Matsubara frequency observables. But by coming up with clever proxies, which have been used in the past, we can shed some light on these questions. So here's what the so-called spectral function looks like. So again, what we really want to understand is whether there's any remnant of a Fermi surface, so to speak, as you go above Tc. Now, as I just mentioned, it's very hard to actually measure or compute a spectral function. So instead, what we can measure is some kind of an integrated spectral function. So this was a trick that was used long ago. So in particular, the imaginary time Green's functions can be expressed in terms of the spectral function as follows. So if you look at the imaginary time Green's functions at a specific value of tau, which is beta over 2, that actually tells you what the integrated spectral function looks like over a window that is roughly the temperature itself. Okay, so this is what the result looks like for this particular quantity at various temperatures for the not so flat band. Okay, let me walk you through this data. So at very high temperatures, at scales of roughly 4 times Tc, this is just a blur. So the green lines actually represent where the non-interacting Fermi surface used to be. Okay, so you see nothing. But as you come just above Tc, you see that this quantity is peaked near where the original non-interacting Fermi surface used to be located. Of course, it's become very blurred. Okay? Now, quite interestingly, you go below Tc through Tc over 2. So this is actually reasonably deep into the superconducting regime. And what you see here are actually the gapped Bogoliubov excitations here. Okay? Again, located near where the original non-interacting Fermi surface used to be located. Okay, so this is the result for the not so flat band, even though this is not really at weak coupling. This is still reasonably strong coupling. Here, the interaction is roughly comparable to the bandwidth, and you still see these features. Things actually become quite interesting when you go to the really flat band, and this is what it looks like. So for the really flat band, you sweep this entire temperature window, and you essentially see nothing. Okay, so it's completely incoherent. There's nothing that looks remotely like even a broadened Fermi surface. Okay, good. So now, again, we can use this sort of a proxy for the spectral function to also compute a proxy for the density of states. Okay, so and what that means is we just take this particular quantity evaluated at a certain time slice and integrate over the entire Brillouin zone, and that gives you a proxy for the density of states. And again, you see that already above Tc, roughly coinciding with the value of the pseudogap temperature scale, this quantity drops precipitously. Okay, so both of these observations taken together tell us that in addition to the spin gap we had found earlier, there is some sort of a gap to even single particle excitations above Tc. Okay, of course, I would emphasize that still there is no long-range superconductivity in this broad fluctuation regime. Okay, so now we have found superconductivity, and we have also addressed certain issues associated with the normal state out of which superconductivity emerges in the strong coupling limit. We still haven't addressed the issues of competing orders. Okay, so the same interactions that are giving rise to superconductivity, do they also induce possibly other kinds of electronic ordering? So the nice thing again about Monte Carlo is that you can go ahead and compute whichever correlation function you want to look at, equal time, and it roughly has this form. So right now we're interested in computing the momentum-dependent correlation functions for a lot of different order parameters. So we have already gone through superconductivity, so let me not go into the discussion of that again. We've also looked at the correlation functions of SZ. That doesn't really show much of a structure, but hopefully even at the back you can see that when we look at the charge response and the bond density wave correlations for the not so flat band, we see some structure emerging. Ultimately, of course, superconductivity always wins for this particular situation, but it almost sounds like the system wants to do something in the charge channel, but doesn't. Okay, so you see these sort of, for lack of a better word, some shallow peaks or small bumps, which don't really amount to much because superconductivity just wins. Now, if you actually pay attention to the wave vectors associated with this particular response, it actually correlates quite nicely with the so-called nesting wave vectors of the original Fermi surfaces. Okay? Now, we can also do the same thing for the really flat band, which didn't have any sharp spectral features when we looked at this proxy for the spectral function. And there, all of these extra features, they have all vanished. Superconductivity just wins hands down, but there is still some kind of an enhancement near q equal to 0 in the charge channel. So it seems like even there's something happening in the charge response. Okay? So to shed more light on this particular aspect, we can just look at the compressibility. And what we find is an interesting feature. So if you focus on this temperature window, which is significantly above Tc, but much smaller than this gap scale to all the other inactive bands, both the pairing correlation and the charge correlation function, or the compressibility, they both show strong enhancement. So here we are plotting the inverse susceptibilities. And if you come from high temperatures, it almost seems like they'll both diverge, but ultimately one of them just saturates, the compressibility just saturates, and you only find superconductivity, okay? So we were quite puzzled when we first saw this, but it turns out it was pointed out some time ago in a very special limit, which is the limit of a really flat band. And when the interaction scale really goes to 0 relative to this gap scale, there's actually an emergent SU2 symmetry that relates the pairing susceptibility to the charge compressibility. And in this particular limit, the BCS wave function for this attractive Hubbard model is actually an exact ground state, okay? So, of course, for our model, this symmetry is only approximate, both due to the presence of the finite finite bandwidth, which is not identically 0, and the finite value of this interaction scale to the gap scale to the other inactive bands. So actually, to see this becomes quite clear when you go to weaker couplings, when both the charge and the pairing susceptibility really almost merge together. Of course, ultimately, in all of these cases, superconductivity ultimately wins. So I'm not going to go into a discussion of this any further for now, but really in this at least intermediate scale of energy scales or temperatures, you can describe the thermal fluctuations of this order parameters, if you wish, in terms of a nonlinear sigma model with a slight anisotropy that ultimately favors superconductivity, okay? Good, so with that, I have, what, like 5 minutes maybe, or 4 minutes? Yeah, so let me quickly tell you about these transport measurements that I talked about. So I'm sure Ashwin is going to talk a lot more about twisted bilayer graphene, and this is probably something people have seen already many times. So just to remind you, you take 2 sheets of monolayer graphene, put them on top of each other, and twist them slightly respect to each other by a small angle theta. So hopefully you can see at the back, this gives rise to some kind of a long wavelength structure, which looks like a triangular lattice. So how does this allow you to change the band structure? So I'm going to show you a quick animation for that. The basic idea is when you twist one layer relative to each other, what you're really doing is twisting the Dirac points associated with each layer slightly relative to each other by an amount that depends on the twist angle. And because electrons can tunnel back and forth between the 2 layers, this leads to an avoided level crossing. And that then, depending on how much you twist and the tunneling matrix elements, you can play around with these bands. So hopefully this animation will work and it will become a lot clearer. So what you will see here now is starting from very large angles where you see these isolated Dirac points, you will slowly peel them out of this entire structure, and an isolated band will emerge near the so-called magic angle, okay, with a very narrow bandwidth. So, oops. Okay. Right, so as you change the twist angle, you peel off these bands, and then when the angle becomes close to magic angle, you get this band, really narrow bandwidth set of bands. So of course, this is what inspired us to think about flat band superconductivity in the first place. Let me just play this again, given that Pablo's students spent a lot of time working, making this animation. So again, you have a set of bands that gets peeled out, and then it comes crashing with a very narrow bandwidth. So now, of course, the excitement was what happens when you partially fill these sets of bands. So of course, in the last 2 years or so, we have actually come across a lot of different surprises, which I don't have the time to go through. I'm going to only focus on a very specific aspect of this transport phenomenology, which is what happens to the resistivity as a function of temperature when you are near certain special fillings. These fillings correspond to half filling of the valence band and half filling of the conduction band. Okay? So of course, this is where the original correlated insulators were discovered back in 2018, and which was soon followed by the discovery of superconductivity. But now if you go to high temperatures, of course, you can ask what is the metallic state out of which all of this emerges? And this is what this particular data is supposed to show you. So if you look at the resistivity as a function of temperature near a narrow range of fillings near this particular insulator, so the color coding here just corresponds to the color coding here, you find that there's a broad regime where you find perfectly T-linear straight lines. So the resistivity scales linearly with temperature, and there's not a whole lot of variation in the slope. Of course, at very low temperatures, the response is dramatically different depending on if you're going into this insulating state or into the superconducting state. Okay? So the question we were interested in is if we can extract some kind of a universal quantity out of this transport data. So one of the things we did was do the following. So suppose you assume that you can still describe transport within Drude theory. Okay? We don't have any better theory for now, so let's just assume this works. So you express the resistivity in terms of the classic Drude type form with the carrier concentration denoted Nc and the effective mass denoted m star. And what we want to do is to extract the temperature dependence of this relaxation time or the relaxation rate. Okay? So given that for these kinds of samples you have independent measurements or some independent measurements of m star and Nc, what we found quite miraculously is that this time scale scales, of course, linearly with temperature, but with a coefficient that's just an order 1 number, okay, independent of the underlying details. Now, this is quite interesting because there are many other correlated systems which also show the same phenomenology, as was pointed out by Andy McKenzie's group quite a few years ago. Now, if you do the same exercise for monolayer graphene, which also shows T-linear resistivity, but for rather simple reasons, having to do with electron scattering of acoustic phonons. And if you do this analysis, you find that this coefficient is 2 orders of magnitude smaller. Okay? So there's something special that happens for magic angle graphene near these very special fillings. Also, what's quite interesting here is that the resistivity does not seem to exhibit any crossovers as you go through the estimated Fermi temperature. Okay? So of course, that brings the question of whether you should treat this fluid as a quantum or a classical fluid. And from the actual values of the resistivities, if you try to extract a mean free path, you soon find that KFL becomes order 1. So again, question of whether you can really treat this in terms of a quasi-particle-based picture. So now, this will be my last slide. Of course, as I already mentioned, in graphene and in also many conventional metals, such as copper, etc., T-linear resistivity is routinely seen. And this is, simply because of electron scatter of acoustic phonons in the equipartition regime. So the question is, can something like this also work for magic angle graphene? And indeed, there were papers written quite early on that suggest this kind of a picture. But I would like to point out that this is not actually settled and certainly far from being obvious. And there are numerous reasons for this, so let me just quickly mention them. So the best case for T-linear resistivity comes only near these special correlated commensurate fillings. So it's a surprise why, if this mechanism is operational, why it should happen at these specific fillings, where also interaction clearly plays some role in giving rise to these insulators and so on. Also, if you actually look at the lowest temperature scale down to which this linearity persists, it's 0.5 Kelvin. Actually, now there are measurements which show this down to 100 millikelvin, which is far lower compared to the characteristic Bloch-Bruneissen temperature scale, down to which the standard electron phonon scenario will give you a T-linear resistivity. Okay? So this really shockingly low scale is something that the electron phonon scale scattering mechanism can't really immediately explain. But actually, one of the most immediate concerns is what the Moiré potential does to the phonons themselves. Okay? So far, we only talked about how the Moiré potential affects the electrons. But actually, it was pointed out earlier this year that this Moiré potential also has some strong effect on the phonons themselves. And if you start from the sort of non-interacting, or rather the phonon dispersions for just decoupled sheets of graphene and turn on the Moiré potential, it actually reconstructs this whole dispersion. So what used to be the acoustic branch of graphene, it gets gapped out and starts resembling an optical-like branch. Yeah, I'm almost done. So now as you sweep through all of these temperature scales, there's no reason why you would see just a single T-linear regime with a slope that doesn't change as a function of temperature. Okay, so here's a summary. So hopefully I was able to convince you that even in this very non-trivial regime where the bandwidth is going to nearly 0, you can still get superconductivity with a TC that scales with few over a broad regime of energy scales. And above TC, we found indications of this pseudogap regime, which had both the spin gap and gap to single electron excitations. Now, of course, what we want to do is now, as I already mentioned, this model really doesn't have much to do with any of the microscopics of these van der Waals systems. And the question is, can we do better now and work with realistic models? One question I didn't touch upon at all, but I'm happy to discuss now, is whether we can say anything universal about the superfluid stiffness. There's been some work related to this in the past year or so. And with regard to the last part, of course, I can go on and on about this, but the question is, do we really understand transport in magic angle twisted bilayer graphene? I don't think we do at the moment, because a simple electron phonon based scenario doesn't really explain this data. Thank you for your attention, and sorry for going over time.
Can I request Subhro to set up while we quickly ask questions? So, questions?
Yes.
Slope has to do with the
compressibility.
bandwidth.
Yeah.
So that's what you see, right?
In magic angle graphene?
Yeah.
No. Because in that story, the linearity won't persist down to this really shockingly low temperature scale, which is 100 millikelvin. That's far below the bandwidth of even the flat band. The band in twisted bilayer graphene has some bandwidth.
What's the bandwidth there?
Okay, maybe order 10 MeV or so.
In milli-electron volt, 100
Yeah.
degrees K?
Yeah.
That's the width of the flat band?
Roughly, yes.
So the surprise is you see the linearity below that temperature.
Oh yeah, far below that temperature.
Yeah, so the fact that TC scales with U in your calculation, it's similar to what you would have expected in the mean field theory.
Yeah.
Is that a complete accident, or do you think there is a hidden reason? Can we sort of conclude that maybe mean field theory would also work because of some cancellation in?
No. So, I mean, yeah, mean field theory kind of had to work, because if there is a solution to the BCS gap equations, there's just one energy scale, which is U. Of course, it's completely uncontrolled, because certain basic assumptions having to do with BCS theory are clearly not applicable here. What really this is telling us, that even in this flat band limit, the reason you're getting this TC with the only available energy scale, which is U, probably has something to do with the underlying topology. If you take a trivial flat band and turn on U, you're most likely not going to get a TC that scales with U. So this original comment that I made with the Wannier functions having some geometric character being fat probably feeds into giving us this non-trivial aspect related to the superconductivity. So the underlying topology, or more accurately, the geometry is playing some role in giving us this particular behavior.
Also, the second question is, what kind of filling did you take? Maybe I missed when you were doing these calculations.
Oh, over all fillings, right? I mean, I even
you tried all. Okay. All right. Cool. Thank you.
Question. So, what was the role of churn number of in your model?
Yeah.
I didn't get. If I consider different churn numbers for this flat band, what differences do you see? If it was 0 versus 1 versus whatever.
Yeah. So in this model, there's no 0. We didn't study the model with the trivial band.
I see. So
we have some preliminary results where trivial flat bands are not giving us anything remotely similar. So that's the comment. You need some kind of topology and distribution, non-trivial distribution of Berry curvature in your momentum space to give you this effect. A trivial flat band with a large energy scale of U is presumably not going to give you this kind of physics.
The TC will still be probably U, right?
No, I don't think you will get superconductivity at all in that case. You can get insulators and other kinds of broken symmetries. What guarantees you that a flat...
With attractive interaction.
Or you can get phase separation and things like that. I mean, sorry, maybe I didn't mention, I mean, the fact that we are also seeing in this model this increased compressibility as a function of temperature, that is a tendency towards some kind of phase separation, which ultimately gets beaten by superconductivity. But if you take trivial flat bands, all kinds of other things can happen. You're not guaranteed to get superconductivity.
But in this old paper by Amber, is it Nandini Trivedi and collaborators? They did, in their case.
No, they were doing completely different stuff. You mean the one I cited from 95? Or?
Yeah.
Yeah, they were just doing something totally different, nothing related to this. I cited that just for adopting this trick of the integrated spectral function.
One last question.
On trivial band, does it have any effect on the kind of superconductor that you realize?
Yeah, so the superconductor here is just a trivial S-wave superconductor.
So it's trivial.
Yeah. No, not at all. So if, in fact, yeah, that's an interesting question. So if you take copper, so copper exhibits T-linear resistivity, again, because of trivial reasons, electron-phonon scattering. And if you do this analysis, you will find that the coefficient is this Planckian, meaning it's some order 1 number times kBt divided by h bar. Of course, copper doesn't become a superconductor. And that's kind of a coincidence because the dimensionless electron-phonon coupling strength is roughly 1. So, yeah, so you have to look at this on a case-by-case basis.
Okay. If there are further questions, maybe you can catch Debanjan later. Let's thank the speaker again.